Hey, welcome. We are back at it with lesson 11-6, and we're really just doing an introduction to hypothesis testing. By the time we're done with this lesson, you should be able to state two hypotheses for a statistical question and decide if the data support one of the hypotheses. The first little bit here is an explore and reason, where we've got a coin toss. And so they've already done the coin toss, coin 1 and coin 2, and we're counting and we're thinking about, like, is this a fair coin? So down in part C is the meat of the problem. Can you conclude with certainty? What does certainty mean to you, Mrs. Conway?
Well, within 5% or so accuracy.
A little wiggle room for a little error.
Yes, especially if I have a small sample like this. But
Small samples.
it should be fairly, if it's 50-50, then it should be about half heads and half tails, I would think.
And that brings us right to the habit of mind. If you got exactly 15 heads and exactly 15 tails, could you say for certain again that the coin was fair?
Well, certain is pretty certain.
It's a hard barrier to cross, and so there still could be a little bit of error there. So we wouldn't want to say with 100%.
I wish it was a calculation I could do.
Oh, well, we probably won't get there in this lesson, but if you go on to take a full-blown statistical class, you will.
Okay, so a car has been getting 34.6 miles per gallon with a fuel, and then with a fuel additive, it gets 35.3 miles per gallon. So what hypothesis would you test to determine whether the increase in mileage is due to the additive? I think we should test two hypotheses.
What two?
Like maybe it did nothing. That's one possibility. Or it did something. So the first step in determining whether the additive is effective is to formulate a hypothesis to test. Determine what your question means in terms of a parameter. The additive works if a car gets higher gas mileage, mean gas mileage when using the additive than the mean gas mileage when not using the additive. So that would be one theory.
Well, but we still have kind of a branch there. It either is doing better or it's not.
State this information about the parameter mathematically. Let mu, again, that's that little u term, represent the mean as gas mileage for the car with the additive. You want to know if the gas mileage is greater than 34.6. This is a hypothesis, which is a possible explanation of one or more of the occurrences. Here's the brand new thing. It's called the null hypothesis. And it's saying what would happen if the hypothesis is not true. If the fuel additive does not cause an increase in gas mileage, then mu is going to stay 34.6. This is also a hypothesis. So the hypothesis that there is no change is called the null hypothesis. And then the possibility that it does something is called the alternative hypothesis. Pretty much every study you've ever done would have a null hypothesis. If you do an experiment and your control group matches what your experimental group does, that means nothing happened. So that's the null, nothing.
But
Yeah. Alternatively, the gas mileage goes up, and so there your treatment or your experiment did something. Notice the little sub-zero, H sub-zero, and the blue right here? You'll see that. That's how they always note the null hypothesis.
And then H sub A is always going to be the alternative. And I appreciate how this is written here because we have both hypotheses. I'm going to just make it so we can write here. But this is the mathematical way that we write both of those things together.
Do you call these the complement? It's either this or that. Like
It's close to that. For now, let's just think about the null hypothesis and the alternative. This either happens or doesn't. And in my class, we talked a lot about how, like, what is a fuel additive? Well, it's something you put in with your fuel to get better gas mileage. So we want to have better gas mileage in this particular case.
Otherwise, it'd be a waste of money. Yeah. What are the quantities of interest? How do you know? We'll let you fill that in.
Well, and we're thinking about this gas mileage, so that's really what we're looking at.
Quantity means numerical.
This is a really nice little add-in exactly one of the hypotheses can be true. And that's what we really have to go back to. Like when we get to the end of our experiment or we're looking at our results, only we want to be able to say that this hypothesis was true or we reject that null hypothesis. It always goes back to the null hypothesis and whether we're going to accept it or reject it.
And if we reject it, we assume the alternative hypothesis is correct. That's got to be one or the other.
Yep. And so in our try it, we've got a slightly different than our example because we've got the soccer girl and she's like, here I am, and she saves 46.4% of her opponent's tie-breaking attempts. I imagine this as a shootout. After her coach says, take 2 steps forward and adjust her position, she's gonna save 47.3% of the attempts. And so this one is slightly different because what we're looking at, oopsies, is we've got either gonna be greater than that 46% or less. So take a look at how they write this. You've got, and this is where we really get into that complement where we're gonna cover everything.
Right. So you wouldn't put the equals with both, for example, because it's just one, there's 100%, it's gotta be one or the other.
We're gonna cover that whole number line with a closed arrow going one way, so that open arrow has to go the other, so we're not doubled up.
And the 47.3 does not go into this hypothesis at all. We're just talking about baseline, like that control. Like if nothing had changed, here's where we would have been. So the hypothesis is that the percentage is less than or equal to 46.4%. So they wrote that as a decimal. And then the alternative hypothesis is that the percent was greater than the 46.4%.
Okay, so we're gonna stick with this fuel additive idea and we're gonna design an experiment. So this is a fairly long example, so stick with us. But we've got this car company and they want to increase a particular type of car's gas mileage. And so with the additive, we've got these as our, oh, wait, that says the words. And so then with the additive, here we are. And so we want to use the data to compare the effectiveness of the additive.
So if there were no difference in the gas mileages with or without the additive, the means of the gas mileages would be equal. So mean means average, so they're just gonna average the first group and average the second group. And if the additive increases the gas mileage, the difference would be greater than 0. So if it went up, you'd see that. Let mu1 be the mean of the gas mileage with the additive, and mu2 be the mean of the gas mileage without the additive. The null hypothesis and alternative hypothesis are, if it's a null hypothesis, there is no difference. So they're just finding the averages, subtracting, and showing that there wasn't a difference. If the alternative hypothesis is true, that the additive helped, then when you subtracted, you would get a number greater than 0.
And they control for the car, like they're all doing the same type of car. And so they've designed this experiment such that we're really looking at the additive and we want to know, is it due to the additive or is it just random chance that these cars got grouped over here and got some mileage, these cars got grouped over here and got some mileage?
And this is only 5 cars of each, so maybe it's not quite enough yet to be sure. So when they did the averages, 0.76 miles per gallon greater with the additive.
So that's what we found with the experiment. We say, oh, you got better gas mileage. But is that enough to actually say that? Or is it due to, like the basketball problem from the previous lesson, to random chance? Or random variation is the use, the official math terminology. So as we go down, it's extremely unlikely to think that all 10 cars would have exactly the same gas mileage. Maybe their tires are more worn. There's just all these small variations. Even if the additive had no effect, we wouldn't really expect to see all 10 have the 2 average, like have the exact same gas mileage. There's always going to be some amount of variation, and I think we just want to keep that in mind. It is possible that by chance alone, and this is maybe a sentence that you might write down, it is possible by chance alone with the higher gas mileage would group together and the cars with the lower gas mileage would group together. Maybe you don't want to write it down. Maybe you just want that idea that it's chance.
the grouping might just be responsible for the difference. So one way to test it is to randomly assign the cars into new groups several times. So we'll do a little activity in class and have you do this several times and find the difference, not based on additive, but just based on grouping. Like if we hadn't even had the additive involved, what would a general most often difference be?
Well, and so how we're going to do it in class, if you've missed class or if you're not going to be able to attend class, what we did is we took all 10 of these different gas mileages and we wrote them on cards. And so what we're going to do in class is we're going to shuffle these up and we're going to put them into two groups. So we pool all of our data values and we're going to put them into two groups and find the mean, assuming that the additive made no difference, essentially. And so when they get this, they get a mean of new group 1, 34.9, and a mean of new group 2, 34.98.
So if there is no difference in mileage between the groups with or without the additive, reassigning the data into two groups repeatedly will likely result in differences closely distributed around 0. If there is a difference in mileage, it's likely to be large variability in the distribution of differences.
While this provides one basis of comparison for testing the null hypothesis, many more resamples and many more comparisons are needed before you can reject the null hypothesis that there was no difference.
So we scrambled up the groups, we scrambled up the cards, and found the difference to only be 0.08. So you'd say, oh, well then maybe the groups are similar, and the 0.76 when we experimented did make a big difference.
Mm-hmm.
But we'd have to do it more and more times to be sure, because maybe that was just a lucky chance that time. Was there something at the bottom?
It's a heavenly. So what they want you to do here, and I'm going to talk a little bit about this, is they said in one particular randomization of one group has these values. So it's got 34.1. So of our original, they're going to take out and put in the group 1, or the additive, you could say, 34.1. They're going to take out 36.7. Proceed?
Yeah.
Okay, so they're going to take out 35.1. They're going to take out 36.1. They're going to take out 36.8. And so they want you to identify the values in the other group. So it's like with the cards, we're now in two groups, and I've shuffled them and pulled these cards out and made two piles. And so this is in our second pile, and they're asking us what's left.
Well, if we're in class, we might just actually pull those out and do it physically.
Yeah.
That's a good idea.
Yeah. So what's left is going to be 33.8 right here. What's left? 33.1, and so on. Then
And these values are not provided in just the workbook. So you'll need to get onto
yes,
the interactive book if
that's
you're
a
at home.
very good point.
Okay, so now you'd find the differences of the means for the two groups. So basically you're just doing another round of random grouping to see what the difference is, to figure out, did the additive actually do anything in the experimental groups?
Yep. And we want to know, like, if the difference between them is 0, is 0.76 an unusual value, or is that pretty typical? So we will proceed to example 3. So we're continuing with the car company, and after reassigning, so fuel additive increased the particular type of car's gas mileage. That's our big question. After randomly reassigning the data twice,
Only twice?
we really couldn't make a conclusion based on that.
How can continued randomization be used to test this hypothesis? So here's steps to follow, and these are very standard steps to follow. What's the name of this? Randomization test. So you put all the data from your experiment, both the treated and the untreated, into a single set.
set.
Create two new groups of data at random from the pool.
I know I'm little up here, but I'm shuffling it up so that I'm pulling them out random. Group A, Group B, Group A, Group B, Group A, Group B.
Calculate the difference of means for the two new groups, which is what you did in example 2, and then record, I suppose it should say.
Well, and I made a table to say, okay, here is my new group 1, my new group 2, and their means. Then we found the difference, and we just made a quick little table, and we did it a couple times to get the hang of it.
And do we do positive differences, negative
Oh,
differences?
we
Does it matter?
Both. That's a huge
So
deal because
should we always do U1 minus U2 or something consistent?
yes. So U1 minus U2 equals this difference between the means. And we really go back to that thought. If it's 0, there's no difference between the treatment and the no treatment. And then I told my class, I said, do it now 10 times, now do it 50 times. And they were like, eyes bulging, like, don't make me do that. Okay, a computer generated this simulation, and what do we find?
So the differences are most commonly are between -1 and 1 here. And so then we mark off with this red line our difference from our experiment. And the big question you're asking is, were my results out of ordinary? And I think you'd say,
No,
the results are right in the normal range.
fairly typical. Like if they were out of the like out of
So thinking of that normal curve, the majority of the data is between
like
the 95% in the middle. Think of that.
if you thought of just the 2/3 and then you thought of the 95%, now you're out.
Outside
And
of that.
if you're in that yellow area, you're like, this is unusual. This isn't due to random chance of the cars being in one group and the cars being in the other. And out there.
So could our difference have been attributed just to natural chance in grouping? I think we have to say yes. So if a small experiment does not give convincing evidence that the fuel additive improved the car's gas mileage, more testing might make a difference. So the null hypothesis was that the additive did nothing. And so I think we have to accept the null hypothesis because our results.
And you will find that the language is a little tricky because the way that you said it made good sense, but the way that our book says it, we cannot reject the null hypothesis.
And so I would say accept that the additive did nothing.
But you'll see this language and you'll have to rethink it a couple of times because we cannot reject it. Meaning,
right, and in an experiment where you had a result that was substantial, you would reject the null hypothesis, which means your treatment did something.
so this question, we really bring it all together in example 4. So we're gonna evaluate a report based on some data. And I was telling my class all about the secret shopper because Mrs. Conway used to be a secret shopper and she would go and make sure that a sign was up or the price was what the company wanted it to be. And so I imagine that they sent out 100 secret shoppers around the country and Best Marketing said, our mac and cheese cost $1.45. When they actually went out, the data that they found was on average, it was $1.65 with a standard deviation of 20 cents. So does this study provide strong evidence that Best Bet's claim is false that their product is $1.45?
So the null hypothesis means the mean price of Best Bet is $1.45 as they claim. And then the fact that it's not $1.45 would be our alternative hypothesis. So step 1, break the null hypothesis and the alternative hypothesis.
Now we're going to calculate the margin of error because there's a little wiggle room.
It depends on the size of your study, how tight your standard deviation.
So here's our formula. We knew that we worked on in 11.5. We put in our standard deviation that we were given, our 100 that we were given.
So this was a quantitative thing because we had actual numerical prices.
And we find that it should vary by about 4 cents plus or minus.
If it's true that you set your prices at, so I just can't help it. I always think of it as kind of a normal curve. If it's true that your price is set at
145.
45, then it shouldn't have gone, is it sample statistic and margin of error? 165 is what they got when they went around town. So their data was at 165. And if we go 4 cents left and 4 cents right, we're at 169 to 161. So then the question really becomes, is 145 within the natural variation?
And this it isn't exactly with one standard deviation, but we're saying, is it within that
Within
margin
margin
of error? So we look and compared the claim to the predicted interval.
And the margin of error is bigger the fewer studies we.
This is right. So compare the claim. The claim falls outside the range of reasonable values predicted by the statistical study. The evidence suggests we should reject the null hypothesis. So
We have
let's
to go back up. The
We
null
do.
hypothesis was that the mean price is what they said.
And
In other
when they
words, no
went out and
changes necessary.
sampled, the margin of error was pretty within 4 cents, but they're 20 cents off, and so they have to reject their hypothesis, the null hypothesis. All right, that's it.
That was it?
Woohoo! Nice. Oh, I suppose we could preview. The try it, but it's very, very, very similar to what we just did. And then I think that's all. Nice job out there. Thank you so much for watching. I hope that you're very successful in your practice of this.